So today we're talking about fetal physiology. Before you understand the CTG, you need to understand how the baby is behaving and why we see the changes that we see on the CTG. So we know that fetal circulation is sitting fundamentally on two umbilical arteries and one umbilical vein. And the umbilical arteries are pumping deoxygenated blood from the fetus, and umbilical vein is bringing oxygenated blood. So this is fundamental. Now we know that the placenta is the baby's lungs. The baby is not using its lungs in utero. Therefore, when the baby has low oxygen saturations, it does not have the capacity to increase the rate and depth of respiration. This is fundamental. Oxygen transfer occurs across the placenta, and the baby metabolizes this to produce water and carbon dioxide. Oxygen is carried by hemoglobin, and the bicarbonate that is produced is dissolved as a bicarbonate in solution and blown off through a reversal reaction in the lungs as CO2. So these are all fundamental physiology. Now, what's the difference between the fetus and an adult? So when as an adult you're tired or you're running out of oxygen and you're gasping for breath, what you're doing is you're increasing your respiratory rate and you're breathing in very deep. So you're increasing the rate and depth of your respiration to maintain your oxygen balance and protect your heart. But the baby cannot do that when the baby is running tired and stressed from all the stresses in labor. A baby cannot increase the rate and depth of respiration because it is not exposed to the environment. So what a baby does to protect the myocardium and maintain a positive balance is to decrease the heart rate. And this is what we see as a deceleration. So a deceleration is a physiological response of a baby to maintain its positive oxygen balance. Now, what environment is a baby living in? A baby lives in a hypoxic environment. Oxygen saturations are sitting about 70% in pregnancy and 30% during labor because of all the contractions and mechanical activity happening in labor. So the baby has adjustments to this. So baby hemoglobin is really high. We know that fetal hemoglobin is also having a high affinity. Baby's heart rate is higher, so that cardiac output is higher. Baby can release oxygen at lower oxygen tensions, and it has significant buffers. So this is a baby's physiological adjustment to the events of labor. However, we know that the placenta is the lung of the baby. However, blood flow to the placenta can be disturbed. And there are so many reasons why this can happen when you have an epidural spinal or caval compression, or when you're bleeding, or during a convulsion or hyperstimulation event. All these events can disrupt blood flow in the placental bed, which is the baby's lungs. So how does the baby react to this? If there's disruption, you cannot have the reversal reaction of bicarbonate to CO2 being blown out and going away. So what happens is that you'll have your carbon dioxide tension increasing and H plus increasing in solution. So initial disruption will result in a respiratory acidemia. Now, an acidemia is not equal to acidosis because the fact that you have low oxygen tension doesn't mean you have low oxygen in the tissues. So the baby can be hypoxemic without being hypoxic. However, if there's disruption for a long time, then the baby realizes that the oxygen I'm getting is reduced. So I have to reduce oxygen consumption. Then it also realizes that I have to be efficient in my use of oxygen. If it goes on, it realizes that no, I cannot sustain the situation. So I have to switch into anaerobic metabolism and produce acids. And if the baby switches into anaerobic metabolism, then you develop a metabolic acidemia in addition to the respiratory acidemia. So what are some of these changes? So when the baby reduces oxygen consumption, what does it do? It stops growing. And that is why you normally will have a small baby when you have chronic hypoxia, because it stopped growing to sort of conserve energy. Reduces its movement. So reduced fetal movement is very important. We know that 50% of stillbirths in all those 50% of cases, and the mother reported reduced fetal movements 24 hours before stillbirth happened. So reduced fetal movements is very, very important in maternity care, and you need to educate mothers that when they have reduced fetal movements, they have to report. The baby will maximize oxygen carriage by becoming polycythemic and improving the efficiency of extraction of oxygen use. So babies who are hypoxemic often have an increased risk of developing jaundice because they are polycythemic. The baby also prioritizes oxygen use in its organs. So it prioritizes the brain, heart, and adrenals. And we understand later on why this is important. It also deprioritizes certain organs like the gut, the skin, and kidneys. And therefore, you understand why there's oligohydramnios, for instance, when there's low oxygen, because then you stop peeing, baby stops peeing. You know why there's increased risk of meconium staining, because then there's low oxygen in the sphincter, reduced sphincter tone, and passage of meconium. You also understand why there's increased risk of necrotizing enterocolitis in babies who are hypoxic. And you also understand why babies who are hypoxic have ashen skin. There's also depletion of glycogen because you switch on from aerobic to anaerobic metabolism. Because of the depletion of glycogen, these babies are at risk of neonatal hypoglycemia. And therefore, a baby who has gone through stress in labor or a baby who is small from chronic hypoxemia is at risk of hypoglycemia and needs to be monitored. And also, the buildup of lactic acid is what will actually cause the damage to the baby's organs. Essentially, most babies will have mixed acidemia, both a respiratory component because it started as respiratory and moved to metabolic acidosis. However, if there's a minor metabolic component, most babies are fine, and the fetus will just adapt by redistribution of blood to the heart, brain, and adrenals. And so you can have aerobic respiration going on centrally whilst there's peripheral hypoxia, and the baby is fine. It's just adjusting to the system. So if the acidemia has a minor metabolic component, then the baby is normally fine. However, if the metabolic component increases, then you have an unwell baby. Again, as the acids build up, there's an increased buildup of H+, and the H+ accumulates at lower pHs. So at the same pH drop, if the pH is higher versus if the pH is lower, the amount of H+ that is produced is more when the pH is lower for the same pH change. And therefore, at lower pHs, there's more damage. So you realize that on the time continuum, as the pH is dropping, the quantum of H+ being released, which is damaging to the fetus, is more. How does the baby respond? So we know that when there's stress, because the baby cannot increase the rate and depth of respiration, it will slow down its heart. So you have a deceleration. Baby will stop moving, so your accelerations will go away. If it continues, the baby will redistribute blood. So to redistribute blood to the heart, the brain, and the adrenals. So there will be a catecholamine surge, and you see a rise in baseline on the CTG. And that's why we'll be talking more in our subsequent lectures that in the CTG, every baby has a baseline. If the baby's baseline was 130 and there's a rise to 150, a catecholamine surge has happened, and the baby is going through the continuum of a gradually evolving hypoxia. So for that baby, there's a decompensated stress going on. There's a compensated stress going on, sorry. And therefore, you are not waiting for the 160s or the 180s before you act. You have to start acting. Again, when there's hypoxia in the brain, there's loss of baseline variability. When you see this, you need to understand the physiology going on. And if you continue and there's hypoxia in the heart, the baseline becomes unstable because the baby cannot sustain the baseline, and there's a collapse, and the baby dies. We also know the baby's heart rate is regulated by the nervous system. So you have an interplay between the sympathetic and parasympathetic nervous system. So the baseline heart rate and variability is maintained by the heart, parasympathetic nervous system trying to reduce the heart rate in response to hypoxic stress. And it also mediates the baroreceptor and chemoreceptor responses, which I'll talk about. Voluntary movement controlled by somatic system. So when there's voluntary movement, you have accelerations. However, we know that voluntary movements, accelerations are seen in anesthetized babies. So there's a component of accelerations which is also centrally mediated. Now, when there's cord occlusion, there's an occlusion in the umbilical arteries. There's increased systemic blood pressure in the baby, and this stimulates the baroreceptors. And the baroreceptors send nodes to the heart via the vagus, and so there's a decrease in heart rate. And that's why cord compressions will cause a decrease in the heart rate. And we call these baroreceptor decelerations. There's a sharp drop and a sharp rise because as soon as the compression is gone, the heart rate rises. So baroreceptor decelerations normally are variable decelerations. When you press on the baby's head too, stimulation of the dura can also cause a parasympathetic vagal response and a bradycardia or a deceleration. So you need to be aware of that, especially when you are doing a fetal scalp stimulation. So there's a light rub on the baby's head to induce an acceleration. If you press too hard on the baby's head, you rather induce a vagus response and a deceleration and a bradycardia. And this is also it tells us why some babies will have an acute bradycardia in the second stage when the head is really compressed through a combination of the contractions and the maternal pushing efforts. When you accumulate bicarbonates and H plus and decrease O2, the chemoreceptors will also respond, and you have a chemoreceptor deceleration. So the chemoreceptors also send vagal stimulation to the heart, and there will be a drop in heart rate. But this drop in heart rate lasts rather long because to reverse it, you need to wash away all the acids in the placental bed. So as against a baroreceptor deceleration, which is a sharp drop and a sharp rise, a deceleration that is lasting long tells you that the baby is trying to wash off acid in order for their response to come back to baseline. So it tells you the difference and understanding of the physiology of why these decelerations are happening. Again, like I said, when the baby is under hypoxic stress, it will stimulate a catecholamine surge. And this is the baby producing adrenaline and noradrenaline to increase its heart rate so that it may be able to pump more blood and use oxygen efficiently. And when you see a rise in the heart rate, and it doesn't need to be above 160, like I said, if a baby's normal baseline is 120 and it's risen to 140, there has been a catecholamine surge for that baby. And you need to understand the physiology and respond appropriately. Because once a compensated stress response has happened from a gradually evolving hypoxia, if you do not act, it will move to a decompensated stress response. You also need to understand that the cost of the catecholamine surge is energy. For the baby to be able to sustain the catecholamine surge and heart beat at that high rate, it needs energy, which is glycogen stores. And it's already started responding to a hypoxic situation. So it's undergoing anaerobic metabolism. So it's dependent on those glycogen stores. If you deplete those glycogen stores, the response will stop. So you need to understand it and know that if you're dealing with a small baby, versus a healthy big baby, the length of catecholamine surge is different. A healthy baby has a lot of glycogen stores and can sustain the rise in baseline for probably hours, 2 or 3 hours, 4 hours. And hours. But if you have a small baby, a growth restricted baby, it can probably sustain it for an hour before it goes into an acute bradycardia and dies. So if you see a catecholamine surge in a small baby, your antenna should be high compared to a big baby. Understanding the physiology helps you to understand this and interpret the CTG better. So to put all this together, understand the clinical picture and what challenges the baby is facing. How is the baby responding? Decelerations, change in baseline, reduced variability. Is there central hypoxia? Is there catecholamine surge? Are you having a baroreceptor or chemoreceptor deceleration? How do we empathize with the baby? Understand the baby's response and act appropriately. And understanding the physiology will help you to know if the baby is coping or not. Thank you.